Great. Thanks, Raj. Thanks for staying. Hopefully everybody has a beer and is, or had a beer and was settled in. What I want to do is actually talk, I'm going to talk about mixed phase clouds, but I'm actually mostly going to talk about an example of a recent collaboration that Jeff Stith and I have started at NCAR, where we're trying to bridge a gap, and the gap is actually trying to figure out how we can better use in-situ observations to evaluate large-scale models, and I'll show some examples of that I think are actually pretty remarkable, and I didn't actually believe we could do this until we tried it. So I want to talk about Southern Ocean cloud model biases a little bit. Obviously that's been discussed, and again, as has already been mentioned, the punchline is that supercooled liquid is a key process. I'll show some examples basically of aircraft in situ data and also some satellite observations. And then I'm going to basically look at some a few perturbation experiments at the end, similar to what Graham showed about how we can improve this. And the status of this is we're sort of working towards a paper on all this. And the key finding is that we can actually constrain model experiments to represent what we see in aircraft observations, and we can use this in a very detailed way to evaluate cloud microphysics. This has been used a lot to evaluate chemistry in models and using chemical transport models, but it hasn't been used too much in climate model experiments, and so that's what I'm actually going to present. It goes without saying, I think, as we've seen, there are significant biases in the current generation of climate models with respect to the cloud radiative effect. There is too much absorbed radiation at the surface. The clouds are not thick enough in the Southern Ocean. The bias has gotten better, but basically there's a huge spread in the models. It's one of the regions of the largest spread of models in this. And again, we're talking about on the order of 40 watts per meter squared. The model I'm going to focus on is the Community Earth System model from NCAR. This is no exception. This is some nice work that HNK led. Recently, it appeared earlier this year, and our model is no exception. That got jumped up. In particular, this is the summer season, and in the annual, basically we're looking at 60 degrees south at on the order of 30 watts per meter squared bias in these simulations. This is present in a lot of models. Graham was showing examples from the IFS system. This is from the Met Office model, some nice work that Alejandro Bodasacedo did, where he basically showed that most of the bias that they diagnose is in the mid-top and the stratocumulus, and this comes from the cold sector, and a lot of these clouds are actually mixed phase, which was what confirms what Graham said as well. So you can see this. What's interesting is if you start looking at satellite observations, and these are CloudSat and Calypso tracks. I've picked out segments of orbit, and what this is a product, the Dardar product from Delano and Hogan, and these, again, like Graham was talking about, I just picked two random segments and looked at one in the Southern Ocean and one in the North Pacific, so this is summer and this is winter. And this is Antarctica here to orient you. This goes from, again, these get jumps, or this is something like 70 south and this is 60 south, so this is across the Southern Ocean in the South Pacific. And this is a product that does the radar and the LiDAR to look at the phase determination. So it looks at the bright bands that appear in the LiDAR to indicate where there is ice, and then it looks at the radar to pick out where the liquid is. And what you can see here is the blue is ice, and the purple is all liquid, and then the red is supercooled liquid. And so there's the signature, and this is, again, we're looking at like 6 to 8 degrees of latitude. So hundreds of kilometers of fairly low clouds with supercooled tops. And in the North Pacific, again, this is now winter, so there may be some issues here with the retrievals right at the surface, but again, the LiDAR seems to be seeing a lot of supercooled liquid. And this is a very interesting product to dive into and to understand how frequent that occurs, and that's not going to be the purpose of this talk. That's sort of some future work. But we want to look at how the model can reproduce this, and do we actually have in-situ observations to try to validate some of this. So what I'm going to do is use some opportunities. Now this was with the NSF G-V, so this was the HIAPER pole-to-pole experiment. And it was basically a carbon cycle experiment, but there was cloud microphysical probes on here, so we do have representations of number concentrations and total water and liquid and ice water estimates. And so we do have the required measurements to do this, and pole to pole, there was a base for these different flights. They went around the Pacific, but they did base out of New Zealand, coming into New Zealand and going south of New Zealand as far as 65 south. And I'll pick out a couple of two flights. One is this, I'll refer to this as HIPPO 3, RFO 6, which is the blue. So leaving New Zealand, sampling, turning around, coming back up at high altitude, coming back to New Zealand. So 65 south, doing profiles basically down to the sea surface. So this is just about the only in situ microphysical data that I know of out over the clean, or not, I won't say clean, pristine regions of the Southern Ocean. Be careful with my terms there. And then here's another one, which is actually in the subtropics. This flight in particular will be in the winter, but again, going down to New Zealand and sampling all the way. So what we've done to try to simulate these cases in a model is to do something that people have commonly done with chemical transport models, and that is we're specifying the dynamics, sort of just, instead of calculating the dynamics, we're nudging the model strongly with a 5-hour relaxation time towards winds and temperatures. So this is the GEOS 5 meteorology. It's 200-kilometer resolution, and I think it's 56 levels. The water species and all the other trace species in the model are advected and conserved. So we put in the dynamics or relax the dynamics, but the water, so the water vapor and the condensed water and all the aerosol species are scavenged or emitted, scavenged, transported as a regular climate model would do it. And I should also note that we've actually, this took a little bit of work, but the climate of this model, because we're running it for 3 years over the whole HIPPO period, I can actually look at the climatology, and we're actually in somewhat radiative balance. So this does resemble Earth, which it doesn't necessarily need to because there is no energy conservation when you force the winds and temperatures. But we've constructed this so we're getting reasonable representation of the clouds. Our global cloud fractions are approximately correct. What we do is we go and output columns from the model. We oversample the model, essentially. We specify the winds and temperatures. If these are model grid boxes with a plane flying through it, we have observations every 10 seconds. We oversample, but what's nice is we have 50 or 100 observations in one model grid box at one time step. And so we can actually get a sense of the subgrid variability that's sampled in the real atmosphere in the model. And so very different resolutions for cloud microphysics. We have one in-cloud value for this entire 200-kilometer grid box, but we have maybe 30 to 50 values from the observations. And when we do that, we actually get something sensible, believe it or not. So this is this one flight, and here's the latitude. So we're headed down to New Zealand. This is landing in Christchurch here. This is taking off in the subtropics in winter. The aircraft is shown here, so flying up and down in pressure. This is just time as the axis. The blue colors indicate ice, the darker gray colors indicate liquid, the greener colors indicate supercooled liquid that is colder than 0 degrees centigrade. And the contours here are from the model, and the crosses here on the flight tracker where the aircraft saw these various condensed species. And the aircraft actually generally puts clouds where the model puts clouds where generally the aircraft finds them, which is pretty nice. And so there's a couple of instances of things being missed here, particularly missing supercooled liquid here. But you can actually see this, and we can also do things like here at 40 degrees south in the winter, we're actually getting supercooled liquid in the model over liquid, so that we're getting liquid clouds that are supercooled. And if you did a scatter plot of this, you can actually scatter plot the number. This is the presence of the condensate. This is the actual number concentration of the condensate. To get it on the same scale, this is 1 per cm cubed, and this is 1 per liter. So this is ice, and this is liquid. And this is really remarkable in the context of trying to understand, are we getting ice microphysics correct? Here we actually have a good representation as a function of temperature of the ice number concentration in the model. So the model is the crosses, the model is the diamonds, the crosses here are the actual observations. And you can see that we're missing, however, significant amounts of supercooled liquid at fairly cold temperatures, -20. We're even missing it here at -10. So what's nice is this segment of the flight is actually the title slide image. So right here, this is from the aircraft when it was in this place, and we're actually looking at the clouds that we're sampling. You can run through this and look at the frontal systems and look at what's going on. So we actually can simulate individual sets of cloud systems. Of course, this only works because we're dealing with synoptic scale systems. If you tried doing this for tropical convection, it wouldn't work at all. But when we force the model with winds and temperatures, we get the large-scale systems in the right place. Here's some observations. So here's 0C. I should note that this is the large particle profile. It's not specifically ice, it's an imager. So there are counts of that, and you can see actually significant amounts of supercooled liquid in the droplet profile. There's also some evidence here of rime splintering. There's a lot of microphysics that we can look at in more detail, even going back to try to diagnose what processes are going on in both the observations and the models. So this is still more to mine here. It's been a very fruitful collaboration. Here's another example. This will be one of the last things I'm going to show. This is a different flight. This is going from Christchurch down and diving into the Southern Ocean at 60, 65 south, and then coming back. And you can see in the deeper part of the Southern Ocean where we see the largest climate model biases at 60 to 65 south. The model is predicting all ice when there is a significant amount of supercooled liquid still present in the observations. Again, we do get supercooled liquid on top of liquid, but we don't really get supercooled liquid on top of ice here. And you can see here, here's the supercooled liquid in the model. We're getting some of it, not quite to the right temperatures as in observations, and some differences significantly in magnitude. Now, one of the interesting things we can do, this is with sort of the base model microphysics. We've actually experimented with trying to we're now using this to improve the physics in the model. And we can do this, but we only have, say, 1 or 2 flights. So we're actually looking at trying to get a lot more data and do better statistics. But we still have a decent amount of statistics here. And so qualitatively, you can kind of play with this. Here's a significant amount of a region where we're actually missing a lot of the supercooled liquid, where we know the climate model biases are. And we can actually compare, we can do this, and we're getting supercooled liquid down to minus 25 centigrade. So here again, this region. And what's interesting is now we can go modify the model. So we're in the process of doing things like putting in a representation of the mixed phase ice nucleation process, which is tied to aerosols. And when we do that, so we're replacing an empirical representation, a formulation that was developed by Myers in 1990 based on fits to mid-latitude data. We're replacing that with something more physical. And you can see here, when we do that, now we start to pick up more of the supercooled, now we start to actually pick up supercooled liquid, not ice, from the model in these regions. And you can see the changes here. We're getting a higher quantity, higher number of concentrations of some of the supercooling and actually supercooling to lower temperatures. And if you look at this globally, so this is now the global bias in a climate simulation, free-running fixed SST simulations. This, again, is the big Southern Hemisphere bias. You can ignore that. I'm happy to, for beer, I will describe this in detail about what's going on in the tropics, but that's not the subject of this talk. You can see this significant bias here. This is what I just showed. When we add the new ice nucleation, we can kind of remove some of this, except around the continent. An alternative formulation is we can add new microphysics, and this is adding prognostic precipitation and representing the snow, rain and snow a lot better. That also, these are not combined, these are separate things. We're in the process of combining them. The issue, I think, is we just don't have a lot. I'm trying to do this by saying, okay, here's one flight, and now I'm going to extrapolate to the whole planet. What would be nice is to have a lot more observations, and we're hoping to be able to go down and do this again and have the opportunity to get aerosol information also when we do this and try to make sure we're getting the right answer here, or a better answer for the right reasons. So in summary, we have new ways of setting up climate models to get closer to observations. They actually work. We can go from detailed observations all the way up to climate in a process-based way. We no longer have to look at, we can actually go to the specific microphysical processes in the individual cases. And in this particular case, mixed phase clouds and supercooled liquid are important. That's consistent with a lot of the other models we've seen. And here we've seen some improvements with the mixed phase ice nucleation is critical. Got some other experiments looking at vapor deposition. That's another critical process. That's another beer that somebody can buy me. And with that, thank you for your time. Thanks for staying.
Any questions for our speaker? Please.
If that's a question or comment, it's really interesting, the talk. I totally agree that we need more measurements available. And we have in the EU project backers actually a work package, or part of the work package, just doing just this. We've done it a bit in the GAF project for aerosols already, harmonizing measurements. And we want to do this with cloud microphysics in concerned backwards distribution.
Yeah, that's great. And I should note that, I think I've noted here, this is a community tool. The nice part about what I've done is we can output only along flight tracks, so I can just about email somebody these files. It's not terabytes of output to get the instantaneous stuff, so it's easy to work with, and other people can run this model with these tools for other projects. I think it's a great, I think it's a great tool, and it actually seems to work pretty well.
Thank you. All right, our next